In this video, we'll learn about storage virtualization and how storage resources are presented to your virtual machines. So a virtual machine is similar to a physical machine in many ways, right? It's got an operating system installed on it. And in this particular case, it's got Windows installed on it. And it needs access to CPU, memory, network, storage, and the operating system does not know that it's running within a virtual machine. So our goal here is to basically trick the guest operating system into thinking that it has real hardware. So we'll provide access to memory, CPU, storage, and networking resources. And essentially, the goal here is to trick the virtual machine into thinking that these are just normal physical resources. So, from the perspective of the virtual machine, and Windows in this case, Windows needs to see drives. When I'm working in the Windows operating system and I'm saving a file or making some sort of change, those changes need to be written to a drive via a SCSI command. And so as far as the Windows operating system is concerned, it needs to see just regular old disks and a SCSI controller, just like a physical Windows machine would see. So here on the far left, we see in our little purple box, we've got a Windows VM, and the Windows virtual machine executes some sort of SCSI command. And we see here it's got a virtual SCSI controller. So Windows has drivers, and it appears to Windows like there's a physical hardware SCSI controller. So when Windows has a SCSI command that needs to be written to the C drive, it'll send that SCSI command to the SCSI controller. Right? And if this were to be a physical system, that SCSI controller would communicate with the local physical disks. But this isn't a physical machine. This is a virtual machine. And so when those SCSI commands are generated and sent to this virtual SCSI controller, they're actually being pumped into our hypervisor. And our hypervisor is what presents all of the virtual hardware to our virtual machine. It's this layer of abstraction between the virtual machine and the actual hardware. And what it essentially does is it decouples the virtual machine from the hardware. Here we see we have one storage adapter shown on the screen here, but there might be multiple storage adapters as well. Right? And there might be multiple physical storage systems that they communicate with. None of this really matters to the virtual machine. Right? The hypervisor can redirect those storage operations to different areas, but the virtual machine will never be any of the wiser. It will have no idea where those storage commands are actually going. It doesn't know if this is a fiber channel storage array. It doesn't know if this is iSCSI. Right? Windows has no awareness of any of that. So we're decoupling the physical storage from the virtual machine. And all the virtual machine sees is a virtual SCSI controller and a C drive or a D drive or whatever drive it happens to be writing to. So those SCSI commands flow out of the operating system through that virtual SCSI controller, and the hypervisor takes over from there and directs them to the appropriate storage location. And the storage location in this case is a VMDK. That's a virtual disk. So for every C drive and D drive and E drive and every virtual disk that a VM has, it's backed by a Vmdk file stored on a data store somewhere. So as those SCSI commands get issued by Windows, this virtual machine has a Vmdk file that the ESXi host is aware of, and that the ESXi host knows where that Vmdk file resides. And so those changes, those SCSI commands, are going to be pumped over some sort of storage network towards that Vmdk file. And in that manner, the changes made by the guest operating system are relayed to the virtual disk of that virtual machine. Now, when it comes to our VMDKs, we have a couple options. Right? And let's say that we've created this Windows virtual machine, and when you're configuring your VM and setting it up, you can choose how big you want the virtual disk to be. And you can choose whether you want that virtual disk to be thin or thick provisioned. Right, so in this case, let's assume that when we were creating our VM, we gave it an 80 gig virtual disk, right? But so far, we're only actually storing 40 gigs of data, right? So it's just like any other Windows machine. It might have an 80 gig disk, but Windows and whatever else we're storing on that disk might not add up to 80 gigs. Right? It might be less. So the actual data that's being stored by this VM is only 40 gigs worth, even though we've given it an 80 gig disk. If we're using a thin provisioned disk, that gives us some efficiency here, right? Because there is 40 gigs of actual data. Well, that's the only space that'll actually get consumed on the data store. So we don't immediately consume all of the space that's allocated to this VM on the data store. It's a much more efficient way to operate. Right? If Windows only needs to store 40 gigs of data, that's all the space that'll be consumed on the data store. And that's what a thin provisioned disk is. A thick provisioned disk is a little bit different. If I create an 80 gig thick provisioned disk, it is immediately going to consume 80 gigs of space on the data store. So why would I ever go with a thick provisioned disk? Well, we now know that a thin provisioned disk saves space. It's very efficient. Whereas a thick provisioned disk allocates 100% of the space up front. And before that space can be used, right, whether we're talking about thin or thick provisioned disks, before any of the space can be used, the blocks that make up that space have to have zeros written to them. Right? So if my virtual machine is about to write some new data to this Vmdk, and it's about to send some sort of new data here, the blocks that it's going to write to have to have all zeros written to them first. And this can take a little time. Right? This is going to consume some storage resources, the actual process of writing out those zeros. So if we are working with a thin provisioned disk, none of those blocks are zeroed when the disk is created. So every time we need to write to a new block of a thin provisioned disk, there's going to be a little bit of a delay there as that block is zeroed out. But thick provisioned disks have all zeros written up front when they're created. So they're not going to have to complete that zeroing operation when new data is going to be written. So for this reason, thick provisioned, eager zeroed virtual disks are recommended for VMs with write-intensive workload. Things like SQL virtual machines or SharePoint VMs. Okay, so in this lesson, we learned that virtual machines are presented virtual hardware, and the guest OS is not aware that it's running on a virtual machine. The guest OS just sees virtualized versions of hardware that it thinks are real. Right. We learned that thin provisioned disks are space efficient, but they don't have the same performance characteristics of a thick provisioned, eager zero disk. So those thin provisioned disks are useful in many cases, and their performance is fine in most situations. But if you have like a SQL database or a SharePoint or an Exchange database availability group, those sorts of applications write a lot of new blocks and should be configured with thick provisioned, eager zero